All right, so section 14.6 is called cylindrical coordinates. One of the things that we saw when we did when we did double integrals is there are cases when polar coordinates were much more helpful to use. In particular cases where we had things that looked more like a circular arc or a piece of a pie, things like that. And so it was very helpful to have this idea of changing x and y into r and theta in certain circumstances, right? Some things we can do in either one, but some things very clearly work better in one versus the other coordinate system. Well, this is another coordinate system. It's called cylindrical coordinates. What cylindrical coordinates do is they replace two of the variables for polar coordinates, and they keep the other coordinate the same. So imagine that you have a cylinder, right? A cylinder means it looks like a circle in one direction, right? R and theta, imagine that. But the height is just this plain old z coordinate, right? Like the can or the water bottle. It's just that same height. So you've replaced, one way to do that with cylindrical coordinates is that you're replacing the x and the y variable in the two-dimensional space with r theta, but you're keeping the z variable as it already is. And there's nothing special about z. You could also do it in the other direction. Like you could replace x and z with r and theta and keep y as it is. So you just have sort of our image anyway would be a cylinder on its side, right? Instead of being the cylinder like standing up and down. So what we're going to do in this section is we're going to do just that. We're going to be replacing two of the variables, and we have to pick which ones are going to be with r and theta, but leave the other one alone. All right, so the integral that we're going to be looking at is that we're going to have an integral over a region Q of f of r theta, and I'm choosing to write this down in terms of z, but it could be written with zx or y, of dv. And what this does when we change this into these coordinates is that we get the integral, and we always have theta on the outside, so kind of just to keep your mind wrapped around that, we're always going to do d theta last. The integral in the middle of this one would be g1 of theta, g2 of theta, and then my innermost integral, they use k1 of r theta, k2 of r theta. And this is of my function f of r theta z. And the order of the integration that I just chose was dz, dr, d theta. And I've left something out. My apologies. Let me put it in here. The piece that's easy to leave out, forget if you will, is that there is a factor of r. Do you remember when we did the polar coordinates that happened? We have the factor of r here as well. So they write it at the back. You could write it at the front if you prefer. So you have f of r theta z times r, and then dz, dr, d theta. And the dz, dr, d theta is pretty much always in that order. So whatever the variable that is not polar coordinates is done first, and then dr is done second, and then d theta is done last. All right, so this is what we're going to be doing. We're going to do an example. We're going to write the given equation in cylindrical coordinates. So the first thing we're going to do is just sort of a step back into polar coordinates for the moment to remind yourselves how to write them. So I've got a few examples in here of that. They won't take us very long to do. They won't take you very long to do in your homework either. So this is not the calculus part of this yet. It's just the changing of coordinates. All right, so the first one we're going to do is z equals x squared plus y squared. So, pretty straightforward. What will this one be? Yeah, just z equals r squared. Okay, so reminding yourself that x squared, I'll write them down to you just as a reminder, x squared plus y squared equals r squared. X is equal to r cosine of theta. y is equal to r sine of theta. And for what we're going to be working with, that's pretty much all we're going to need to be using. That's going to be one of those three. There's a couple other coordinate changes you can make, but those are the three we're going to be using. Let's try a second one, a little more complicated. What if I had x minus 2 squared plus y squared equals 4? What shape is this? In 2 dimensions, it would be an ellipse. So this would be if we've got the value z doing whatever it wants. Huh?
That's a little circle.
It would. Oh, you're right. It is a circle. In 2 dimensions, it would be a circle. So then, yeah, off-centered. Exactly. You're right. And then if it were in 3 dimensions, then this would be a cylindrical. It would be a cylinder, actually, right? Because their z value could be anything, because there's no restrictions on what can z be here. So this is actually a cylinder in 3 dimensions. All right, so, but I can't just sort of like pluck the -2 out. I actually have to FOIL that to make this work. Agreed? So if I FOIL this, I get x squared minus 4x plus 4 plus y squared equals 4. So something nice happens. What's nice? The 4's cancel. And then what did you see, Nathan? You said about the squares. Okay. So like putting this, did you put the squares together? Is that what you mean?
Yeah.
Like that? Would that work?
Yeah.
Sure, that's exactly what you meant, right? Why would it be nice to do that? Because that's r squared, right? X squared plus y squared is r squared. What about x? Well, it's r cosine theta. And we're going to solve this for r. In the problems that we're going to be working with, having things solved for r is a helpful thing to do. So if I solve this for r, I would move r to one side, or even you could even factor. Let's do it that way. Let's factor. R times r minus 4 cosine theta. Does that look okay? So we end up getting r equals to 0 and r equals to 4 cosine of theta. So in particular, when we're looking for limits of integration, that would be helpful, wouldn't it? Because we'd have a lower limit of 0, generally speaking. Well, not necessarily. Depends on the thetas that we're using. But we have one limit of 0. You know, I guess with r it would be a lower limit of 0, and then the upper limit would be 4 cosine theta. All right, let's do some calculus with this now so you can see how this plays out. We'll do one problem, and then we'll stop. All right, so we're going to set up the triple integral. We're not actually going to solve. We're just going to set up. Set up the triple integral over the region Q of f of x, y, z dv in cylindrical coordinates. And our region Q is the solid above z equals square root of x squared plus y squared, and below z equals the square root of 8 minus x squared minus y squared. Now, we haven't actually seen one that doesn't do this, but let me just make a point to say we get to pick which variable we keep the same, and z is the right one to pick here because you see that the x squared plus the y squared, both positive squares, are already in the problem and can be replaced very easily with r squared, right? So we are eliminating the x squared and the y squared when we're working with this particular problem. We won't always do that, and you'll see that very shortly in the next lesson, or in the next time we meet. But we can start out by changing these into what they are in terms of r and theta. So what in the world is z equals the square root of x squared plus y squared going to be in polar coordinates? Yeah, this is just z equal to r. What about the one down here? The square root of 8 minus r squared, which does not simplify readily, right? So, all right, so we're going to be looking for an integral now of q, over q rather, of f of x, y, z dv. And this is supposed to be an integral between different coordinate system. And I've got a function. I'm not given a specific function, but my general function I'm working with is going to be in terms of r, hang on. Yeah, that's left out. So the variables that I'm replacing, the x and the y, are going to be in terms of the polar coordinates. So x is r cosine theta, and then y is r sine theta, and then my z is the one that I'm keeping fixed. And this is times r. I'm going to put dz on the inside, and then dr, and then d theta. So let's go back and take a look at limits of integration. The inside limits of integration on z need to be taken into consideration the z equal r, and the z equals the square root of 8 minus r. I need to know which one's above which one, or I need to draw a picture of the two of them to try and figure it out. You can use your calculator if you'd like. You don't necessarily need to have them, I don't think you need to have it in polar coordinates to see it. We just need to know which one's larger. So is z equal r going to be larger, or is z equal to 8 minus r squared going to be larger? Not sure?
What are you asking?
I need to know where the r and where the square root of 8 minus r squared go. Which one's on top and which one's on bottom? Right? I need to put them here and here, and I need to know which one I put where. Okay, let's try this. You guys are staring at me like I have just stepped off the moon. In terms of, well, just plug in a number actually would work just fine. What if r is equal to 1? Then which one's bigger? Yeah, this one's bigger, right? I need values bigger than 1 anyway, and my values can only get so large. They can only get so large that I don't have a square root of a negative number underneath there, right? So r equals 1 is a good test point, I can see. So Jordan just told me that r is smaller. Is that what you said? And then the square root of 8 minus r squared was larger. Is that right?
Yeah, I'm confused. Couldn't you just know that because it's above and below?
You could, yes, you're right. I'm sorry, I forgot that those directions were given to us before. You're right, above and below. On this one. Yep. They don't always say above and below. Sometimes they'll say trapped between. But you're right, on this one they gave us more information. I'd forgotten about that. Okay, we need limits of integration on r. So there are limits on what r can be. Okay, obviously r can be anything in z equal r. R cannot be anything in square root of 8 minus r squared. So what is the smallest value for r? It's 0 because r is the radius, right? So we're looking at 0. What's the largest value for r? Can't be 4. Square root of 8. That's exactly right. Or if you write it simplified, it'd be 2 square roots of 2. That's my upper limit for r. And then what in the world is this shape? I mean, what does z equal the square root of x squared plus y squared? I mean, let me say it a different way. We need to look at for my limits on theta. What would be my limits on theta?
0 to pi.
0 to 2 pi. Yeah, all the way around the circle. Okay, we'll stop there.